Welcome everyone to another workshop for the Middle Era Hackathon series. We are here with Dustin, our developer engineer at ZKsync. So glad to have you here and so happy. The floor is yours. Give us an introduction about yourself because you're new to our team also, so that the developers of ZKsync can kind of know more about you and get used to see your face a lot.
Yeah. Absolutely. Well, thank you for having me. Really excited to be here. I do have a slide that I do a little brief of myself, but thank you all for attending. Again, really excited to be here and speak to you today about state diffs. The title of this presentation is Maximizing Efficiency with State Diffs in ZKsync Era. And we're going to kind of go through some contract design considerations based on this approach. And yeah, I'm just super excited. So I am new to the MetaLabs team. I'm part of the DevRel team. We kind of have a mission not only to help build ZKsync, but to educate developers on the unique features and tooling and kind of technical differences that make up ZKsync Era. This is something I'm truly excited about and passionate about. I do have my GitHub handle there at DataButter if you want to follow me there. I just re-entered the Twitter sphere, brand new to the Twitter sphere at DataButter92. If you could give me a follow, that would certainly help. I'll certainly be providing more updates on ZKsync and our future developments there. So so let's just kind of kick things off and get right into it. So what we'll be kind of discussing today is kind of a general agenda here. We're going to start with a general overview of ZKsync Era. This is either an opportunity to provide a refresher to those already familiar with the topic, or for those unfamiliar with ZKsync Era, a great introduction too. We'll progress to establishing an understanding of state diffs, what that means, why we publish state diffs, and some of the use cases that can be achieved with this approach. We'll briefly touch on alternatives to state diffs and go through some of the unique characteristics of each approach. Then we'll discuss some smart contract design considerations and end with some practical examples of a simple Oracle contract that we kind of further optimize relative to these design considerations. Of course, if you have any questions, please feel free to ask. I will do my best to answer. If I don't have the answer for you right now, I promise I will search the ends of earth to get you to that answer. Don't hesitate to ask. Let's jump right in. So what is ZKsync Era? Well, it is a general purpose layer 2 rollup that scales Ethereum using zero knowledge proofs. It is powered by a ZK EVM with native account abstraction. Kind of discussing that in a little bit more granular detail. ZK rollups bundle transactions into batches, which are verified for correctness on Ethereum or an L1 network. After the verification passes, the batch of transactions is considered final, like any other Ethereum transaction. This is achieved through the power of validity proofs. Once a proof is generated, it's submitted to Ethereum to make that rollup batch final. And if you're not really sure what account abstraction is or want to get into more details about ZK rollups, I highly recommend checking out our docs. They're a fantastic explainer of a lot of these technical topics that goes into deep. And also there is a fantastic video of my colleague Antonio going into account abstraction on YouTube. It is fantastic. I highly recommend it as well. So ZKsync Era, a layer 2 rollup powered by ZK. So what does that really achieve for us? Well, it increases Ethereum scalability by moving transaction execution off chain. This happens on the L2. We reduce transaction fees by bundling all these transactions into batches, and then we generate that state validity proof and verify it on the L1. So kind of to recap, this is how ZK rollups work. We generate a proof that the transaction is executed in the L2 produced a new state. We then verify that proof on the L1. This is how zero knowledge proofs is used to secure the system and inherit the security of Ethereum. We have language support for Solidity and Viper for contract development, as well as compatibility with the Ethereum API. So the development flow for developers remains the same. All those contracts you've written on Ethereum can be deployed right on ZKsync Era, which is awesome. And all accounts in ZKsync Era are smart contract accounts. This is amazing. You can now pay gas fees in tokens. With paymasters, you can write a contract that handles the gas costs for your users. And if you're want to kind of explore more use cases relative to paymasters, we do have this awesome paymaster examples repo on our GitHub that you can see some more interesting flows. There's one there, the ERC 721 gated paymaster. This is an awesome one. This allows the paymaster to pay gas fees for users that have or possess a certain NFT. Definitely go check it out. There's a lot more examples there. So that's kind of a very quick overview or summary of ZKsync Era. But again, this presentation is about state diffs. So what are state diffs? State diffs represent the differences between the chain slots in a given batch. Let's unpack that a little bit. The term state, of course, refers to the current snapshot of all account balances and other data stored on chain. Now consider a batch of transactions that changes this state. Instead of recording all the details of the new state, we can just keep track of what has changed from the old state. These are state diffs. So state diffs or differences refer to the change in the state caused by those transactions. This technique reduces the amount of data we need to store and transmit. Instead of needing to handle the entire state, we're only dealing with the changes. So Era only posts the state updates after a batch of transactions is sealed. So updating the same storage slot multiple times is inexpensive. Let's kind of think of an example. If Alice transferred, oh, we got a raised hand.
Your slides are not changing. So maybe you're sharing a screen with slides on the first page only.
Wow, that's embarrassing. Thank you for updating me there. Awesome.
Don't worry.
Yeah, I thought it was gonna auto, but it clearly did not. All right. Now everyone sees the correct slide. We'll kind of continue. So Era only posts the state updates after a batch transaction is sealed. So updating the same storage slot multiple times is inexpensive. So an example, if Alice transferred ETH to Bob repeatedly within the same batch, we'd be updating the same storage slot multiple times. And since we only publish the final state diff, we would only incur fees once here. That's tremendous. That's awesome. And then, of course, publishing state diffs ensure the data necessary for constructing and verifying the state is available on L1. This is a very important property that will be repeated throughout this presentation. Of course, it's important for others to be able to validate the correctness of the L2 state, and we will need to have the data available on L1 so users can access their funds, for example. Let's look at an example. Here, you can see kind of an example to illustrate the benefits of this approach that is publishing state diffs. Now, this is a very oversimplification of a verifier contract. And I mean, very oversimplified, but it captures a key difference in the state diff approach. This contract takes an input of a large array of data. You can think of it potentially being an array containing a new state root, an old state root, and other data elements. And the verifier contract that takes this large amount of input data is going to be very expensive on other L2s where the gas model requires paying for all that transaction call data. Using state diffs, we can verify these proofs rather inexpensively. That is a kind of a oversimplification of just this kind of unique indifference, but it's an important one to illustrate. So now that we kind of are experts on state diffs, why do we publish state diffs? What's kind of the reasoning here? Well, efficiency is a key property of why we publish state diffs. Only publishing the final state changes saves space and resources. Again, consider a batch of transactions that changes the state. Instead of recording all the details of that new state, we can just keep track of what has changed from the old state. That is efficiency. Cost effectiveness. State diffs are more economical as they omit publishing unnecessary data, like interim changes to the same slot, signatures, etc. Less data, lower fees. Data availability. We talked about this already. It's going to be repeated. State diffs ensure the data necessary for constructing and verifying this L2 state is available on L1. This is, of course, a requirement for any rollup. You need to be able to verify the L2 state. Without it, no one can really validate the correctness of that state. Use cases. So this is what I'm most excited about. We discussed the cost optimization of our kind of very oversimplified verification contract. However, by leveraging state diff, we can power up a new era of Web3 application development. I like how I snuck the word era in that excitement, because that's certainly we're in kind of the precipice of a new era of Web3 application development. So let's talk about those use cases a little bit more. We have oracles, trading, verification of zero knowledge proofs. These are awesome use cases that we're already aware about, but now we can kind of further draw them out to be even more exciting and useful. For oracles, we unlock the ability to update data points much more frequently. Since on ZKsync, users only pay for the changes in storage, and more precisely, only a final state diff is again published to the L1. Oracle updates to a shared storage slot are much more inexpensive. Think of updating prices more frequently, perhaps temperature, live scores, whatever imagination can kind of run deep here. For trading, frequent dexes or perpetual trades save substantially, as multiple same slot updates in a transaction batch incur no extra cost. So kind of an example perhaps is like a lot of these trading solutions allow batch transactions. So you can make 100 trades, then pay the cost of those 100 trades. However, you're still paying the gas cost of those 100 trades. In a state-based system like ZKsync Era, if you make 100 trades in the same asset pair, say ETH USDT within a batch transaction, it would not only be treated as a single transaction, but also a single storage slot update, further reducing cost, which is awesome. Verification, again, we touched on this very briefly at the beginning with our oversimplified contract. Less data to store means lower cost. State diffs will facilitate more widespread usage of privacy-preserving applications on chain. That is going to be exciting. We haven't really seen really strong applications there, and we're definitely going to. And then anything that requires repetitive storage slot updates, like developers can optimize transaction batching to further reduce fees by strategically grouping transactions together. They can maximize cost savings and benefit from state diffs. I encourage all developers out there to get creative, be imaginative, and think outside the box of being able to utilize and leverage this approach for their kind of future applications. Of course, there's alternatives to state diffs. This is publishing transaction call data, otherwise known as inputs. This includes publishing the full transaction call data on L1, all the details. All executed transactions are submitted to an on-chain smart contract. This ensures data availability, just like state diffs, as all the necessary data to verify the correct state is available. This is an approach used by Polygon, ZK and Scroll, and others. That's kind of a very high-level summary of publishing transaction call data. But let's kind of look a little bit more into some of the unique characteristic differences between the inputs versus outputs, or transaction call data for state diffs. We kind of have 6 categories here. What they represent: data published on an L1, data availability, finality, verification process, and cost. Kind of going through each, you probably already have a pretty good understanding, but detailed information about each transaction is what inputs represent, whereas in outputs, the final state difference after all those transactions in a given batch are executed are what is published. Again, the data published to the L1 for inputs, it's that full transaction detail. That's a lot of data. Whereas in outputs, we only publish the final state to L1. A lot less data is transmitted. Data availability. So with inputs, all the necessary data to recreate the state is certainly available. For outputs, all necessary data to recreate the state is also available, even with the consolidation of changes. That's awesome. There's a slight differences in finality. So inputs offers a slightly faster finality guarantee because all that transaction data is available immediately. Whereas in the outputs, might take slightly longer due to the need to publish and verify the validity proof. Kind of to recall, each update to the system state must be accompanied by that ZK proof. This ensures that the new state was derived by correctly applying a series of valid user transactions to the previous state. Once that proof is processed on Ethereum, the L2 block is instantly finalized. So there's a slightly longer, but still achieves the exact same approach of finality. The verification process, we kind of hit on this. For inputs, full nodes can verify the data independently as soon as the data is published on the L1. Again, it contains all the transaction details. And whereas in the outputs, the outcome of a transaction can only be determined after a related validity proof is published and verified. But the major difference here that I really want to highlight is that inputs, for inputs, data, this is much more of a resource intensive approach because you have to publish all the transaction details. More resource intensive means more cost. Whereas in outputs, it's much more cost effective as we only publish that final state diff, reducing the amount of data published to L1. This is also very cost effective for contract redeployment. Example of this is like a DEX with a pair factory contract for different pair pools. This contract bytecode of a pair is only published when the first instance is deployed. After that, subsequent deployments only involve updating one storage slot, which sets the contract code hash on the newly deployed pair address. So this is an example of that cost efficiency between the two. So let's get into more of the fun stuff, which is the contract design considerations. So like Ethereum and any blockchain, the most costly operation is storage updates. So to leverage the state diffs, there's kind of like four main parts that you want to consider when you're designing your contract. Update storage slots as little as possible. That is just because, again, the most costly operation is storage updates. We want to reuse as many storage slots as possible, as that really leverages the benefits of state diffs. Of course, reuse contract code where possible, and we want to clear those storage slots that are for temporary use. And we're going to go through a series of very simplified Oracle contracts that demonstrate this from a very non-optimal approach, where we can see these design considerations not really being considered, and then going into a slightly more optimized approach where some of these design considerations are enacted, and then finally a far more optimized approach where a lot of these design considerations are considered and implemented. So of course, we got to start with what an example of what not to do. So this is, I don't know if you guys can see the code very well, certainly let me know. This is a contract of a simple Oracle that updates the storage with every price update. This is not efficient. There's excessive storage slot updates happening here. You can see in the update price function, updates the storage slot every time a new price is updated. This means that for like frequent price updates, the number of state changes will be high, leading to a lot more gas costs. We're not really using storage slots quite efficiently, as there's like a separate storage slot for every data provider, which isn't very efficient. We're not clearing temporary store slots or really reusing any store slots either. This is an example of what not to do. So let's kind of progressively optimize that same type of contract. Here is a kind of further optimized simple Oracle contract with some improvements made. So now the data providers update the temporary price mapping, which is much more optimized because it's less store slot updates. The aggregated price is updated only once all the data providers have submitted their price. So you can see that here in the finalized price. So this contract reduces the frequency of store slot updates by using that temporary storage mapping temporary prices. And we're also clearing temporary storage, which is also part of those design considerations to consider. We are still not really reusing storage slots very well. We can further optimize this so that we are really considering all those design considerations and really taking advantage of the state diff approach. This is kind of highlighted in this kind of super optimized simple Oracle example. And super here might be certainly an exaggeration, but it does introduce further improvements by packing that data provider's temporary price and kind of unique ID into this data provider struct. So we're reusing store slot for each data provider with this data provider struct. We are clearing temporary storage slots after each use in finalized price, which is awesome. And we're really utilizing the key design considerations of reducing storage updates, reusing storage slots, and clearing temporary storage slots. This is kind of how one might be able to leverage those state diffs approach to further optimize their contracts and really try to optimize for gas costs for their users and their application. Yeah. So key takeaways, ZKsync Era uses state diffs for data availability. Only the final state diff is published to Ethereum. This makes many use cases a lot cheaper to execute, which is super exciting. There's cost savings for applications with frequent storage updates, like we mentioned, oracles and trading and verification of ZKPs. And of course, you have to should always consider the smart contract design considerations to really optimize your contracts for this state diff approach. We're going to update source slots as little as possible. We're going to reuse as many storage slots as possible. We're going to reuse contract code where possible, and we're going to clear storage slots that are for temporary use. If you are interested in kind of next steps, you can certainly check out our documentation at era.zksync.io docs. There's a migration guide. We have a number of tutorials that provides a great walkthrough of paymasters, account abstractions, deploying contracts. For users, certainly check out our ecosystem, our bridge, join our Discord, follow us on Twitter. And if you are a developer with certain specific questions for ZKsync Era, you can definitely check out our developer discussions page on GitHub. Thanks so much for the time. And yeah, happy to answer any questions. But yeah, it was a pleasure presenting for you today.
Thank you, Dustin, so much. It was an amazing presentation. And congrats on your first presentation for the team. We do not have any questions for now, but for all of your future listeners who will listen to the workshop, make sure to use the comment session. It will be there for everyone who has questions, and we'll get back with all of the content that you need. And for now, have a great day and have a great journey for the hackathon. And yeah, do let us know if you have any questions in all of the socials that we have. Thank you.